Okay, I thought we'd go over one more example so we could see one that we really don't know what the graph is going to look like. So we really have to rely on our calculus to figure out what's going on. So if we look at this function, I see that we have 6x to the 2/3 minus 4x. When we talk about the domain of a function, we're really worried about, do we have an even root where we can't have negatives under the radical? Do we have a fraction where we have to worry about dividing by 0? Neither of those things are happening in this. We do have a root, but it's of 3. So we really don't need to worry about what we can or cannot plug into x. Our domain's going to be all real numbers. Okay. Since we do not have a rational, we don't have to worry about asymptotes. So our points of discontinuity can be brushed to the side on this one. And we can go straight to end behavior. Okay, so remember, end behavior, we're talking about what is happening to the right of our function and what is happening to the left of our function. Okay, now, some of you might not like this because we're talking about an example that's not purely polynomial. Okay, we can, however, view this limit. This isn't a polynomial, but we can still use our polynomial rules because our highest degree is of degree 1. So we can look at that coefficient of -4, and that can help us determine what's happening. If that makes you a little bit nervous, I will never know if you look at your increasing, decreasing intervals first and then fill in the limit at the end. So if you're unsure about a limit and you want to come back to the end, that is okay, but I would obviously prefer you to do it right away, so that can help you when it goes into your graph. But if we look at that -4, that would tell us that towards the right we would be falling, and towards the left we would have opposite behavior. Okay. Intercepts. On the examples we did yesterday, our intercepts really didn't take us much work. This one might be a little bit different. At least for our y-intercept, we can see that if we plug in 0, we're going to get 0. Okay, well, what about our x-intercepts? We need to set our function 6x to the 2/3 minus 4x equal to 0. Okay, now we're not really used to factoring with anything like this, but we can look at this and say, you know what, we do have a GCF. Okay, we have a GCF of 2x to the 2/3. And I know that feels a little uncomfortable, but there is a 2/3 power in this x to the first power. Okay, so if we factor out 2x to the 2/3, here we'd be left with 3, minus here we'd be left with 2, and then if we divide out an x to the 2/3 power, that means there is an x to the 1/3 power left, because x to the 2/3 times x to the 1/3, our exponents would add together to be x to the first power. Okay. So this is going to give us x equals 0, this factor right here. This factor over here is going to give us 3 minus 2x to the 1/3 equals 0, which means 3 equals 2x to the 1/3. We can divide that 2 over, and to get rid of that 1/3 power, we would cube both sides. So we have 27/8 as our second x-intercept. So we have an x and y-intercept at 0, 0, and then we have 27/8, 0 as our second intercept. Okay? And that's all of our pre-calculus work that we have to do. Now let's actually get into the calculus of all of this here. So our first derivative is going to tell us where our function is increasing and decreasing, and also if we have any maximums or minimums, we'll find them here. So our first derivative, if we do the power rule, 6 times 2/3 would be 4, x to the -1/3, and then -4x has a derivative of negative 4. Okay. In order to be able to compare this to 0, okay, I know that some of you want to like set it equal to 0 and figure it out right away, but since we have that negative exponent, I'm going to encourage you to write that as a fraction. And since we care about both, where this is 0 and undefined, I'm going to go ahead and have you write this as a fraction. So in order to make common denominators, this is going to need an x to the 1/3 power in the denominator. So we have 4 minus 4x to the 1/3 over x to the 1/3. So we can see that our critical points are 0 because that's where our denominator would be 0, so our derivative is undefined. And then also at 1 because that is what would make the numerator 0. So if I put these on a number line, we would get intervals of negative, positive, negative for our first derivative, which means we would have a minimum at x equals 0 and a maximum at x equals 1. Okay? We already know that 0, 0 is our coordinate. Well, if we plug in 1, we get an x value of 2. Now we need the second derivative, okay? Let's be efficient with our work. I know that this is what we got for our simplified first derivative, but I don't really want to take a quotient rule if I don't have to. Come up here where we took the derivative in the very beginning before we simplified it. That was just a power rule. And if I take the derivative from up here, then I would really just need a power rule. So our second derivative using our power rule would be negative 4/3 x to the negative 4/3, and that's it. Okay. So our second derivative would be negative 4 over 3 x to the 4/3. Okay. Well, there is no place that this second derivative is 0. But there is one place where it is undefined. Okay, at 0. No matter what we plug in, both sides of 0 are going to have a second derivative value that is negative. Because of this x to the 4/3 power, it's not going to actually change our values when we plug it in. So we do not have any points of inflection. Okay, we are going to be concave down the whole time. Now, let's come back to our second derivative and think about something. Okay, right here where we decided where we had critical points, 0 was a critical point because it made our first derivative undefined. Well, if we don't have any points of discontinuity and we have a place where our derivative is undefined, what is happening there? There's going to be a corner. We have a place where it is not discontinuous, but our derivative is undefined, so we're going to have a corner. Okay? So when we go over here, to make our graph, I'll just continue on here, I guess. When we come over here to make our graph, okay, we had an intercept of 0, 0, and 27/8. Okay. 0, 0 was also one of our minimum points. Also remember that at x equals 0, our derivative is undefined, so we're going to have a corner there. And then at 1, 2, we have a maximum. Okay. So our calculus tells us we need to be decreasing, increasing, decreasing, but we need to be concave down the whole time. So here I have concave down the whole time. I have a corner at x equals 0 with a minimum and then a maximum at the coordinate 1, 2.